Okay, today we're going to start talking about thermodynamics and thermal physics. We're starting a new unit. I will warn you, this is a lot less intuitive than what we did in the previous unit. Students typically have a tougher time understanding thermodynamics. And that's because our body isn't really designed to measure temperature and interact with thermodynamics. All right, what does it mean for something to be twice as hot? Why does the temperature you feel depend on whether you're sitting or running, right? Someone comes inside from exercising and they say, oh, this room is really hot. And you're sitting there working on your computer and you say, actually, I feel kind of cool in here. When you pick up a piece of plastic and a piece of metal at the same temperature, maybe the plastic feels warm, but the metal feels hot, right? Our body is not really good at measuring temperature. It's very much less intuitive than, for example, length. If I showed you two pieces of string and said this one's twice as long as that one, you could look at them and say, yes, they are, right? That comes intuitively. But this is also what I really like about thermodynamics. You can take things that are not intuitive and still figure them out. Using principles of physics, using math, you can figure things out that don't come naturally to you. And I think that's really empowering. So here we go. What is temperature? In order to measure temperature and understand temperature, we need some sort of instrument to measure it, right? Because our body is just not great at putting numbers on temperature. So we use things like thermometers. And most thermometers that you will encounter will either be marked in degrees Fahrenheit or degrees Celsius, all right? Which one do we use in the SI system? Well, it turns out we don't use either of them because they're both screwy. All right, this little degree sign right here in front, that right there is to let you know that these are screwy temperature systems. You see the degree sign? The degree means screwy. What do I mean by screwy? 0 is arbitrary. All right, 0 is not the lowest temperature you can get to. Imagine, if you will, that I have a meter stick and 0 is in the middle of it. So I go and measure something and I say, oh, this is -3 centimeters long. It doesn't make any sense. Something can't be -3 centimeters long. But in the degrees Fahrenheit, degrees Celsius, we can have things with temperatures that are negative. That doesn't make any sense. That's crazy. All right, so the degrees sign means relative to some weird arbitrary 0. So in SI units, we use Kelvin. Kelvin. Represented with a K. Notice that there is no degree sign in front of it because it's not a screwy system. And when you read, if you measure a temperature and it's 35 Kelvin, you do not say degrees Kelvin because it's not a screwy system. It's just 35 Kelvin. Kelvin are real units. 0 Kelvin is the coldest anything can get. It's known as absolute 0. At 0 Kelvin, something has no thermal energy in it. All the thermal energy has been taken out. All right? And it turns out that 0 Kelvin is equal to -273.15 degrees C. All right? That's absolute 0. Now, it takes more than just a 0 point to define a temperature scale. You also need to know how far apart the markings are on your thermometer, right? And it turns out that Kelvin uses the same spacing as degrees C. So in Celsius, to go from ice melting to water boiling is 100 degrees, right? That's a 100-degree change. Kelvin uses the same spacing, so to go from melting ice to boiling water is also 100 Kelvin. All right? So whenever you see temperature in an equation, you should think Kelvin. If you use something else, chances are pretty good you're going to get the wrong answer. It's not going to work out. Absolute temperature must be in Kelvin. All right? But if you look at a temperature difference, it turns out that Kelvin and degrees C are identical. If you calculate, if I ask you, what is the temperature change from ice melting to water boiling? That's 100 degrees C or 100 Kelvin. It's the same. All right? What is the temperature difference between absolute 0 and ice melting? That's 273.15 degrees C or 273.15 Kelvin because they're both temperature differences. So for temperature difference, Kelvin and degrees C are the same. but whenever you have an absolute temperature, you must use Kelvin. Let me say that again. Absolute temperature, you must use Kelvin or your equations won't work. This is one of the biggest mistakes that students make when they take exams, so pay attention. All right, now we're going to talk about thermal expansion. All right, things expand when you heat them up because temperature has to do with stuff wiggling microscopically. Imagine, if you will, being BYU, we like to pack as many students as we can into a classroom. We want as many students as possible to have the BYU experience. We don't like to waste space. So how can we pack students into a classroom more efficiently? If the students are standing straight up with their hands to their sides, we can pack an awful lot of them into a classroom. But if the students start wiggling and bumping into each other, moving their arms around, then they're going to take up more space. And that's kind of what happens to materials when we heat them up. As we heat them up, the microscopic stuff that they're made out of wiggles more. And as they wiggle more, they take up more space. And that's why things expand thermally. Now, it turns out there are some strange objects that actually shrink when you heat them up. And there are some things that when you heat them up, they'll expand in one dimension but shrink in another. But for the most part, when you heat stuff up, it expands, and it has to do with this wiggling stuff. All right, now how much does it expand? What equation would we use to figure that out? Well, it turns out that the amount that something changes depends on the length it starts out with. Lengths all change by the same factor per degree. So if I have something that expands a certain amount, if I double how much I have, it expands by twice as much. All right? So every linear dimension, if one linear dimension expands by, a part in 10 to the fourth, every other linear dimension will expand by a part in 10 to the fourth. All right? We'll talk more about that in a minute, but here's the basic equation that we'll be using. The change in length of an object is equal to alpha, which is the linear expansion coefficient for the material it's made of, times its initial length, times the change in temperature. All right? Now, we can take this equation and start plugging things in and working homework. But if we haven't derived the equation and understand the assumptions in it, we don't really understand the equation. Now, rather than deriving this equation, rigorously step by step, I'm just going to prove to you that this is the only equation it could be, given the assumptions we're going to make. So basically what this equation says is change in length is equal to something that depends on the material times length times change in temperature. It turns out actually calculating from first principles how things change can be really hard. It involves quantum mechanics, solid state physics. It's difficult, all right? But the reason what we're going to do is easy is we've stuck all the difficult stuff into this linear expansion coefficient. All the particulars of the material in there, I just want to show you that the other parts are true, right? That we multiply by the initial length and the change in temperature. So to show that this is the only equation that this could be, all I have to do is explain why the change in length should be proportional to the initial length and why it should be proportional to the temperature change, not the temperature change squared, the logarithm of the temperature change squared, or the temperature change and whatnot, all right? So the first one's pretty easy. Why should the change in length be proportional to its initial length? Well, imagine I have a bar with a length L naught. And imagine I have another bar that's made of exactly the same material, but it has a length of 2L naught, right? Now let's imagine they're both at the same temperature, and then I heat them both up by some amount. Well, this one's going to expand by some amount. How much is this one going to expand by? Well, let's pretend like this long bar is really two shorter bars stuck together. This one's going to expand, and this one's going to expand. So the amount that this one expands is going to be twice as much as this one because it's really like two bars stuck together. If I had one that was 3 times as long, it would be like 3 bars stuck together, and it would expand 3 times as much. So I think it's pretty easy to see that how much my bar expands by is going to be proportional to the length it started at. All right? So we've figured this one out. Next, we need to know why it would be linear in temperature change. How does that happen? Well, it turns out, strictly speaking, it's not. Imagine that you went to some solid-state physicist and you said, use the best calculations you can possibly do and calculate what the length of this copper bar would be as a function of temperature. All right, so here's absolute 0 Kelvin, here's room temperature, whatever. And imagine they calculate something and it does something like that. I don't know what it would really do. I haven't done this calculation, all right? I'm not a solid-state physicist. But let's imagine that they came back with something like that. And you'd look at that and you'd say, that's not a straight line. Our equation is wrong. Or let's imagine that you went to an experimentalist like me and said, I want you to measure the length of this bar as a function of temperature. So I get it really cold and I measure it and I warm it up and I see how it changes and I get some plot. You look at that plot and you say, that's not a straight line. That equation must be wrong. Well, the point is the equation, this equation, delta L is equal to alpha L naught delta T. The assumption is we're only going to use this equation for very small changes in temperature. For changes in temperature such that we get very small changes in length. All right? So if I just look at this plot and I only look at a little tiny piece of it where the temperature changes a little bit, if I zoom in on that, it looks like a line. If I zoom in over here, this looks like a line. All right? So as long as delta T is small, I expect the length change to be proportional to the change in temperature to the first power, because as I zoom in, it looks like a line. Well, the slope of that line is going to be different if I'm doing my experiment here or here, though. So it turns out that this linear expansion coefficient is actually a function of temperature. So when you go to work a problem, you want to look up a linear expansion coefficient that is valid at the temperature that you're doing the problem. All right? Now, your book gives a bunch of linear expansion coefficients, and it turns out for most things over most temperatures we'd be interested in, it doesn't change very fast. So you can just go ahead and use the values given in the book for all the problems that you work on the homework or the exams. All right. What about area change? What if I wanted to calculate how the area changed with temperature? What is that going to depend on? Probably based on our previous discussion, you're thinking it's probably going to be some constant times the initial area times the change in temperature squared, right? Because if linear expansion goes as change in temperature, the change in area ought to go as change in temperature squared, right? Because like if I have a square, its area is proportional to the side length squared, right? Well, it turns out this is not true. This is wrong. Kick that out of your mind. It turns out it's proportional to delta T to the first power. Why? For the same reason. If I were to plot the area as a function of temperature, if I look at some little region in there for a small temperature change, I just get a straight line over that region. If I zoom in to a little small change in temperature, I get something that looks like a straight line. And so it turns out the change in area is also proportional to delta T, not delta T squared. And you can actually calculate it from our initial equation. Let's imagine I have some plate and I heat it up and it expands. Now really, when we expand things, right, you take an aluminum plate and put a torch to it, you don't see it grow a whole lot, right? So these are really small changes. I'm kind of exaggerating this. But let's imagine I start with this plate and it grows. So let's say this plate has a width W, a length L. So this we'll call delta L, and this distance here we'll call delta W. All right? So the change in area is just this right here, right? But let's divide this into three pieces and we can put this together, all right? So the change in area is this plus this plus this. This area right here is just going to have an area delta L times, well, let's call this L naught and W naught, okay? Then this is delta L times W naught. This one right here is going to have a length of L naught and a width of delta W, right? And then this little piece right here is going to have an area of delta L delta W. The first thing we're going to do is we're going to throw that away. Why? Because these changes are really small. This is really small, this is a little small, really small, and this is really small times really small. Really small times really small is really, really, really small. Okay? Right? 10 to the minus 4th times 10 to the minus 4th is 10 to the minus 8th. I take two small things, multiply them together, I get something really small. Here I have something small times something big, small times big, and here it's just small times small. So this is inconsequential, we'll throw it out. All right? Then, what is delta L? Well, delta L, we know that. It's just the linear expansion coefficient, L naught, delta T. And what is delta W? Well, W is a length, just like L. It's going to follow the same equation, just with W's instead of L, right? So there we go. We plug this in and we get, okay, delta L, that's alpha L naught delta T W naught, plus L naught, and delta W is alpha W naught delta T, and this then is just 2 L naught W naught alpha delta T, and L naught W naught, that's just the original area, right? So this is just 2 alpha area naught delta T. So it looks just like our linear equation. It's still linear in delta T. The only difference is we got a 2 there in front of our linear expansion coefficient. Turns out for volume, you can do the same calculation and you find that it's equal to 3 alpha initial volume times delta T. All right? Now, 3 times alpha, we call that beta. So 3 times the linear expansion coefficient is what we call the volume expansion coefficient. All right? We don't have a special label for 2 times alpha. Well, why would we? Doesn't make any sense, right? If we know the linear expansion coefficient, we can calculate the change in area. We don't need anything else. All we need is alpha. But why do we need something special for volume? That's kind of weird. Let's talk about that for a minute. So imagine if you go out in front of the football stadium and you see the statue of Cosmo the cougar, right? Here's Cosmo. He's got some eyes and a ferocious mouth with fangs. There we go. And a tail. All right, so here's Cosmo. We find out Cosmo's made of bronze. We look up the linear expansion coefficient for bronze near, room temperature. And then we say, okay, what's going to happen if I heat Cosmo up by 10 degrees? Well, I can use my equation, my linear expansion coefficient, my linear expansion equation, and that'll tell me how the length of Cosmo changes. All right? I can also use that equation to find how the distance between the ears change. The distance between the eyes, how they change. Any linear dimension on Cosmo is going to expand according to this equation. That's an important thing to point out. Some people think, oh, the ears will expand, and so they'll expand on top of each other and get closer together. Or the distance between the legs will expand, they'll get on top of each other, and they'll get closer together. No, that's not true. The distance between the legs will expand according to this equation. Every linear dimension will expand according to that equation, because the whole thing expands together. All right? If I wanted to, calculate the surface area of Cosmo, or if I draw a little square on Cosmo and say, well, how is the surface area of this square going to change? I can use this equation right here, right? And I don't need to know anything more than the linear expansion coefficient. If I look up the linear expansion coefficient for that material, that's all I need to calculate the change in area. If I wanted to calculate how the volume of Cosmo changes, or how the volume of his tail changes, I just use this equation there. And all I need is a linear expansion coefficient. I don't need anything else. But now, instead of Cosmo, imagine that you have water in a container. And let's say that this container does not expand thermally very much. I heat up the water, what's it going to do? It's not going to expand such that every linear dimension follows this. No, the water is going to expand and it's going to fit the shape of its container, right? So this equation doesn't make any sense for water. I can't calculate, can't use that equation to calculate how much the width of the water changes. The width doesn't change, right? Because a liquid can change to fit its container. So if with a liquid, it doesn't make any sense to talk about alpha, the linear expansion coefficient. For a liquid, then, it makes sense only to talk about the volume expansion. So if you look in your book, in the table of thermal expansion coefficients, for solids you will find that a linear expansion coefficient is given. And with that, you have everything you need. For liquids, it doesn't make sense to even talk about a linear expansion coefficient, so instead, a volume expansion coefficient will be given. All right, they'll give you beta. All right, so now you know how to deal with liquids and solids, but gases are different, right? Because if I take a gas and I say I heat it up by 10 degrees, how much does its volume change? Well, its volume could change a lot, or it could be in a rigid container and the volume doesn't change at all, just the pressure goes up. So the equations we were looking at before are not enough to tell us about what a gas does. But it turns out we've got another equation which is really good, and it'll describe things over a much wider range of temperatures than the equations we were using before. All right? So now I'm going to tell you about ideal gases. So we're going to come up with an equation that describes ideal gases. Now real gases are a little more complicated, so we're going to stick with ideal gases in this class. So let me tell you the properties of an ideal gas. Molecules in an ideal gas collide like billiard balls. I don't have two hydrogen atoms that come together and then stick to make a molecule. No. I have hydrogen molecules that bounce off of each other like billiard balls. I don't have hydrogen molecules that bump into each other and one of them splits apart into hydrogen atoms. No, I only have elastic collisions in an ideal gas. Also, in an ideal gas, molecules don't occupy space. All right? They're infinitesimal little point particles that bounce off of each other elastically. Another property of ideal gases is that they never condense into liquids or solids. All right? And another property of ideal gases is that they don't exist. Ideal gases don't exist. However, ideal gases are a very good approximation to a lot of things that we do. Take the air in the room surrounding you. Do those molecules collide like billiard balls? No, sometimes they'll bump into each other and one of them will get some energy stored in angular momentum as it starts to spin a little bit more. Or maybe a molecule forms or breaks apart. But on average, energy is flowing in and out of these molecules in a way that cancels out, right? The air in your room is in equilibrium. So molecules are forming at the same rate that they're splitting apart. All right? So inelastic collisions, on average, sometimes they absorb energy, sometimes they give energy off, and on average, they kind of act like billiard balls. The molecules in the room, in the air in the room around you, they do occupy space. But if you took all of the air in the room around you and liquefied it, the volume of that liquid would be very small compared to the volume of the room. The molecules occupy space, but not very much. All right? So it turns out that the ideal gas law does a very good job of modeling the air in the room. Now, we have to assume that the molecules don't condense into liquids or solids. So if you started cooling the air in your room down to the point where the nitrogen started to liquefy, the ideal gas law wouldn't work very well. The humidity in the room will start to liquefy at even more reasonable temperatures, but hopefully there's not enough humidity in the room and we don't get cold enough that that's not a problem. So it turns out you can do a lot of physics with the ideal gas law that really is a good approximation to a lot of real situations. Okay, so here's the ideal gas law. I'm going to give you two versions of it. First of all, here's this version. PV equals NKBT. All right? So this equation, you can derive it using fundamental physics, or you can empirically go and just make a lot of measurements. Put a gas in a container whose size can't change. You're going to hold volume fixed. I double temperature. The pressure doubles. Okay, good, right? I put it in a container that's completely elastic, so it's always at atmospheric pressure, but the volume can change. I heat it up. I see how the volume changes. You make these empirical measurements, and you come up with this equation, all right? Now, the N here represents the number of molecules in your gas, right? K sub B is Boltzmann's constant. It's the proportionality constant. You do these measurements and this comes out, all right? So it's just a number with units. It's just a constant we put in, all right? And this equation is really useful. It tells us, right, if I have a balloon, let's say I have a balloon. Balloons, the pressure of the air inside of a balloon is typically really close to atmospheric pressure. Because if it wasn't, right, the rubber of the balloon, it's very weak. If the pressure inside the balloon was much higher than atmospheric pressure, then it would stretch until it popped. If it was much lower than atmospheric pressure, the balloon would shrink. All right, so a balloon, pretty much, the air is pretty close to atmospheric pressure. All right, so this tells me if I want to double the volume of the balloon, I have to double the temperature, right? Because pressure is constant and the number of molecules in the balloon is constant. K Boltzmann is constant. So the ideal gas law tells me if I want to double the volume of my balloon by heating it up, I have to double the temperature. Well, remember, this is an absolute temperature. What units does the temperature need to be in for this equation? It needs to be in Kelvin. Kelvin. All right? What is room temperature in Kelvin? Turns out it's about 300 Kelvin. So if I want to double the volume, I have to double the temperature, which means the change in temperature, where did my pen go? Delta T is 300 Kelvin, all right? Which is, once again, it's a temperature difference, so I can also write this in Celsius, 300 degrees C. All right, so you have to get it pretty hot to double the volume. All right, so that you can use the ideal gas law to find all these different things. If I hold the pressure constant, change the temperature, how does the volume change? I hold the volume constant, change the temperature, how does the pressure change? And so forth. All right? Now, it turns out that the air in this room, there's just lots and lots of molecules. Molecules are really, really tiny. So oftentimes, instead of talking in terms of the number of molecules, we'll talk in terms of the number of moles of molecules. So if I take the number of molecules and divide by Avogadro's number, 1 mole is 1 Avogadro's number of things, then I get the number of moles of air molecules. All right? And it turns out Avogadro's number is really, really big. All right? So even though there's lots and lots of molecules in the room, that's a small number of moles. So it gives us a number that's more simple to deal with. All right? So if I wanted to rewrite the ideal gas law in terms of moles, then I just say, well, PV is equal to, well, N is going to be the number of moles times Avogadro's number times K Boltzmann times T. And then what we do is we say, look, these two are going to always be together in this form of the equation, so let's just multiply them together and call them R. And then I get PV is equal to nRT. And the little n is the number of moles, big N is the number of molecules. There you have it. All right, so what are these constants? Boltzmann's constant is 1.38 10 to the negative 23rd joules per Kelvin, and R is 8.31446 joules per mole Kelvin. Why these units? Well, it turns out, as we're going to find out later on, pressure times volume has units of energy, joules. All right? So this guy here, when I multiply by temperature, N doesn't have any units. When I multiply by temperature, it needs to give me joules. So it's going to have units of joules per Kelvin. R, right, N does have units. It has units of moles. So R has units of joules per mole Kelvin. That's why these units. Now, why does R have such a reasonable size? K Boltzmann is really, really tiny, but R is of order unity. Well, that was by design, right? We intentionally divided the number of molecules by some numbers so that we'd get a reasonable number of moles, all right? A reasonable number to deal with. So that makes R have a reasonable number as well. That was the whole idea. So how big is a mole? A mole is about 6 times 10 to the 23rd. If the Earth was made out of baseballs, how many baseballs would it make to pack together and make a sphere the size of the Earth? Well, take the radius of the Earth, the radius of a baseball, and divide them, all right? Or divide their volumes, and the volumes, of course, go as the radius cubed. This 0.74 has to do with the fact that as I pack baseballs together, there's air gaps between them. So it takes fewer baseballs because in addition to the volume of the baseball, I get the air between them. All right, so it's a packing efficiency. But you do this calculation, you find out it only takes about 8.6 moles of baseballs to pack together to make a sphere the size of the Earth. So Earth is gigantic, baseballs are small, but it only takes about 8.6 moles. How many moles of pennies do we have to stack to get to the moon? Well, take the thickness of a penny, the distance to the moon, divide the two to find out how many pennies it takes. 2.5 times 10 to the 11th pennies. That's only 4 times 10 to the minus 13 moles. A tiny, tiny, tiny fraction of a mole of pennies will stack to the moon. All right? Moles, Avogadro's number is really big. How many moles of water molecules are there in a liter of water? Well, it turns out there's 55.5. Whoa, that's a small number. Yes, because molecules are really tiny. We chose Avogadro's number to be what it is specifically so that in reasonable amounts of stuff there were reasonable numbers of moles of molecules in them. All right, so molecules are really small, Avogadro's number is really big, and they cancel out so that in a reasonable quantity of stuff you have a reasonable number of moles. By the way, if I turn that liter of water into steam at 100 degrees C at a pressure of 1 atmosphere, it would occupy a volume of 1,685 liters. Right? We said that in an ideal gas, the molecules don't take up space. In a real gas, they don't take up much space. All right? But so, yeah, the molecules are going to be very far apart in this gas, in this steam. All right? But still, right? 1,685 liters is small compared to the volume of the Earth, right? It's still sort of edging on reasonable. By definition, Avogadro's number is the number of carbon-12 atoms in 12 grams of carbon-12. All right, so chosen to be reasonable by design. So, what does the ideal gas law tell us? How much do I have to heat up a balloon to double its volume, double its diameter, right? It's all in there, and I'm not going to go on any longer and talk about this, but I mean, you can learn all kinds of things, right? If I want to double the volume at constant pressure, I have to double the temperature. If I want to double the pressure at constant volume, I have to double the temperature, right? So if you know how any of these are changing. You know, any two of these are changing, you can find how the third one changes. All right? You could also, I'm not going to work this, I'm going to leave this as an exercise to the reader, but how many molecules are there in a spherical balloon with a diameter of 20 centimeters? See if you can figure this out. So you're out at the elementary school selling balloons to the kids at 10 cents a piece. But you decide, hey, here's a better business model. Instead of selling them per balloon, I'm going to sell them per molecule. How many molecules are there in that balloon? Calculate that out. It may surprise you. Anyway, that's the end of our presentation.